would you like to start, Ramon?
Yeah, so I think the plan is I have 2 lectures. The first is to set up this assignment and people ask questions. And then once we feel like we got to start there, then I'll move into a lecture on strike slip faulting geomorphology. And then I'll stop at 11:15 to be sure to reserve Rich half an hour. Is that okay with you, Rich?
Yeah, that's fine.
Okay.
And I can adjust if you go over a little bit, it's fine.
But I'll probably, if I have stuff that rolls over, we'll touch on it on Tuesday next week. So let's go ahead and get started. Let me make sure I've got the right file here. Yeah, okay. So, and I'll try to keep track of the chat, or maybe Chelsea, you can interrupt me just as we go.
Yes.
So this one is, it's called Introduction to the Landers Earthquake. Sometimes we call it strike slip pre-rupture mapping assignment. So it's basically looking at the area in the Mojave Desert where the 1992 Landers earthquake occurred, but looking at data from before that earthquake. And so it's a really interesting example of what we're trying to do in this class. And afterwards, when we go over it, we'll see, we'll show you what was done. So please just avoid any review of the Landers earthquake, because as soon as you see something, you can't unsee it. So the idea is to work without prior knowledge here. The other thing about this assignment is to give you another tool in your toolbox, which is, we've talked about the morphologic mapping. We're working on the GIR. And now we want to also talk to you a little bit about superficial geologic mapping, or mapping the young units in the landscape. And these are well suited to mapping from the remote point of view. Of course, we'd all would like to go in the field, but we won't in this class. So the idea of superficial geologic mapping, or sometimes we call it quaternary geologic mapping, is that we map mostly unconsolidated materials that have been deposited over the quaternary, which is the last 2.5 million years. We discriminate these units by relative elevation, degree of surface modification, soil development, color, incision, so cross-cutting relationships. So a lot of times we see kind of an incision history over time. So the younger units tend to cut the older ones. And another thing that's often a little bit confusing is that in many cases, the younger units are lower in elevation. Now, when you think about stratigraphy, usually you're like, okay, well, as it deposits, it gets higher and higher. But a lot of times what we see in these systems, in these landscapes, is that we have aggradation and incision, and we may have a net case of kind of stepwise incision. And so we're cutting down over the quaternary. And so that's just something to keep in mind. You can, stratigraphic ordering still works. It's not like we're turning physics upside down, but we just have to be aware of kind of what's going on. And that paradigm of a sort of steady down cutting or episodic down cutting is one that's often used. So mostly the tertiary and older hard rock units are mapped as bedrock. So unlike traditional geologic mapping, where we might kind of treat everything with the same level of detail, we tend to lump the old rocks because we don't care about them, given that our question is really about the active or recent history of the landscape, and in particular, what that might indicate for faulting. And the final point, which I've alluded to already, is that there's likely modulation of these surface processes by changing climate, and that will help drive the development of the deposits and landforms. And in shorthand, it's kind of a balance of sediment supply and transport capacity. So high supply, low capacity means aggradation. Relatively low supply compared to capacity means incision. But these two are modulated by quaternary climate. And that's shown just, of course, we could lecture for a long time about the climate history of the Earth, but this shows if you start at C on the right side, this is the longest time scale. It's the last 2 million years of the marine isotopic record of kind of seawater temperature, which is delta 18. And we know that the quaternary is dominated by rapid variation in climate. And so as you go, the middle is kind of the last 800,000 years. and then the left is the last 350,000 years. So we're up here at the very top on this left A column, where, let me just get my little annotation tool. This was the last glacial maximum about 20,000 years ago. It was quite cold, and now it's quite warm, and it's getting warmer thanks to anthropogenic processes. But this modulation shown here in the ocean is global. Let me just see, what did we get in the chat? Any question for me? Underburden, yes. I like that. Yeah, so underburden meaning kind of the bedrock, whereas we're talking about the overburden, which is the young material. Okay, so let's keep going. So, I'll come back to this. So what kind of mapping? So we've taught you, and hopefully now in your toolbox, you feel like you could use morphologic mapping to help you document components of the topography that indicate these features. And now we're going to talk about geologic mapping with an emphasis on these younger materials. So let me just keep going. Sorry, it's kind of awkward sometimes using the annotation tool. Okay, so the way I'm going to explain this is using an example from the Mojave Desert, which is where Landers comes from. So this is a geologic map from the U.S. Geological Survey. That's Reheis, Meredith Reheis, is a very well-known quaternary scientist. And this is not where your assignment is, but it's nearby. And it has some faults in it. And so the colors show the main units, and we'll go into them in a moment. But there's just a couple of bedrock units, which are the purple and the kind of tan, and everything else is quaternary or superficial. So let's zoom in. Let's first look at the units, because this shows the kind of system we're gonna use a simplified version of this. And so if vertically is time, so it's kind of relative age, although they do have some absolute ages in here. So you see the right side shows the rough geologic time. And then the different columns are different environments. So man-made, lacustrine, fluvial, alluvial fan, playa, or kind of local depressions, and aeolian units. And then each one of these, we start off, the first letter is Q for quaternary, and the second letter is the relative age. So QY, QI for intermediate, and QO for old. So you see that like in the alluvial fan case, then A would be the third letter, A. So QYA, QIA, QOA. Now, if we're in more of a fluvial system, if we really know we're in the fluvial part of the landscape, then we might use a slightly more complicated nomenclature, or we just put an F instead of A. And then lacustrine, we would use an L. And for P for playa, and AE for aeolian. But so what we'll see, we have a suggested version, which is the simple, kind of first three letters, whereas you see they go to 4 sometimes with a number. So they're just kind of finer and finer discretization of the different mapping units, but we want to keep this simple. But we're going to try to use this as a standard approach to help you do this mapping. And so here's an example from their map, and you can see here what I want you to appreciate, and it takes time to get a feel for it, but the lower left is the bedrock. And then as we come out, this I don't know what color this QOA is, it's kind of a orangey, like a mustard color, is the old units, and they're basically kind of alluvial material that accumulated in the mid or early Pleistocene around this topography, and it's been actually incised a little bit. So the old units are so old that they're already being modified by younger processes. And then on top of that, in this case, is QYA older, so that's kind of lumped on top of the QOA units, but then cutting down into them is the QYAY. So again, this kind of relationship that's defined to a large degree by height, but also or relative elevation, but also we're accounting for the aggradation, which is the QYA, which is on top of the QOA. So sometimes if you struggle a little bit with these, you can also, just draw some simple kind of topographic profiles, just even without the data, just to kind of sketch out what this might look like. And then in this case, there's a little fault that cuts through that is they see maybe indicated by some of the truncation or disruption of some of these features, and would also be supported by morphologic indicators, kind of like in this case, there's a kind of the end of this scarp right here sort of stops, or the ridgeline stops in a sort of a short scarp. So there's the termination of a few morphologic features that helps indicate that. Yellow or ochre. Thank you, Rachel. And then, so let's look at another one, and then I'll get to the main assignment. So here's another place. This is the Mannix fault in this area. And so here we have the TVS, so tertiary volcanics plus bedrock against these quaternary units. And on the left would be that there's a granite. But again, we're sort of seeing these different quaternary units that are truncated along this active fault. And some of this is supported by field work, so you have to give yourselves a break if you're not seeing everything, but a lot can be done, and a lot is done by interpretation of remote imagery. So let's take this. So that was the pretty map with good cartography. Here it is now. I downloaded, I didn't have a good layer file for this, so this is just their line work, sort of transparent over the color imagery from ARC. So this is not QGIS, but ARC based imagery. But what you can start to maybe appreciate is how they differentiated these units. So, if we start in the younger part, the QYAs are these incised active alluvial systems. Maybe this should really be a QYF because it's almost the fluvial, but that's okay. Then there's this kind of intermediate, this QIE. So this is an intermediate Aeolian deposit that's sort of parked there. That's not probably active because it's not a QYE, but it's something they felt like they could identify, maybe in this case by its light tone. And then up here we see this QYAO, so this older young unit, which has, you can see some of the continuous surface on top. So it's the old alluvial fan surface that has a smoothing that occurs, and then modest incision cutting into it, and also maybe some darker desert pavement helps define that surface. But that's on top of the QVG. So there's like a thin veneer of the alluvial unit that's on top of these QVG, which is an older kind of volcanic gravel. And then in this case, the QOA is what they map as older quaternary, and it's kind of completely incised. It's no longer preserves its original surface, except maybe up here at the very top, we see a little patch of maybe a preserved old fan surface there, but mostly we're on the side here where it's been eroded into. So one of the challenges.
Or sorry, no, finish that sentence.
Just a second. Yeah. Thanks for interrupting me though. The challenge, of course, is reading elevation from imagery, and you just have to get a sense for the texture of the topography. Like here's a little drainage network, so we know we're going down from this crest line here into the main channel. So okay, let me look at the chat and let's talk about this a little bit. Okay, older desert alluvium is darker because of deflation, rocks interlocking, or desert varnish. So two things happen. One thing is a physical reconfiguration of the surface called a desert pavement. And it's kind of a long history of how pavements form, but it's kind of the diffusion of that surface smooths it. And at the same time, many of the clasts that are on that surface accumulate a varnish. And so we get a pavement, but it's both dark in color and relatively smooth compared to the young, fresh alluvial fan surfaces. And it's part of how we know a lot of times the intermediate age surfaces have good pavements, because they're sort of high, they're no longer active, but they're not so old that they've started to be dug into and eroded. So that's why the OA might have at one time had a good pavement, but most of the pavement's gone. So hopefully that helps. More question? Okay, let's keep going. You know, certainly learning by doing, you guys will be able to play with this out in the landers, although it'll be a little more challenging because it's a black and white photo, not color, but it'll work fine. So unlike the sort of relatively complex and fine-grained view of the units from REHISE, we've kind of simplified them a little bit, but we've also pulled some of their units that we think make sense. And so, you know, there's fluvial deposits, which would be QYF or QOF. And some of these are more of the geological description that you might see in the field, but also help with some of the morphology. So QYA is an active young alluvial fan unit. QIA is intermediate, but has well-developed desert pavement over 80% of the surface. And QOA is old, but sort of degraded and broken into. And then QTGU is fanglomerate, QP is playa, TVS and BR are bedrock. And so you guys may not be able to tell the difference between the volcanic and sedimentary rocks and the bedrocks. You could just call it all bedrock. And so for the assignment, what Rachel has done is, first of all, she made a really nice little video that's pretty comprehensive. And so you should just watch it and it'll get you started. But the idea in this assignment has 6 components. The first component is to play with Earth Explorer for imagery surface sources. So this is not really about landers. It's basically go somewhere else, but on the theme of using imagery rather than topography. And then 2 is download the imagery that we're providing you for pre-rupture from landers from 1975. The earthquake was in 1992. And then map the quaternary units as I have hopefully demonstrated to some small degree, and I'll talk a little bit more. Then map the geomorphic features / GIR, and then delineate the fault trace that you infer into 1 kilometer segments and indicate confidence. So remember, you don't have to find faults everywhere, and you can be conservative, but hopefully you'll find something. But just put yourselves in the mind of the geologists in the 70s and 80s mapping in the Mojave, trying to identify active faults, and then boom, 92, there was a pretty big earthquake that broke there. And so the question is, how well was it anticipated using this approach? So I'm gonna go, there's a little bit of back and forth here. I won't address those chat items so much right now. So a couple of hints also. So here we are in QGIS, and so you're given this little polygon to try to fill. And so you can basically see the landscape is this bedrock cored mountain surrounded by these piedmonts. And so that's what you're mapping, is basically one of the piedmonts. And so if I just give a couple of hints, whoops. Oh, so sorry, before I talk about the hints, just the idea of mapping and image interpretation is really, you need to get the most you can out of these images. And there's a lot there. So think about shape of features, size of features, the patterns, tonal contrast. So tonal means kind of relative brightness or darkness of features. We'll see the tonal contrast is a big issue here. Texture, so how sort of smooth or rough is a certain zone. Shadowing helps us with relative height. The site, kind of what to expect in general. This is a Piedmont in the desert, so that should help us. Association. Resolution, so this is not a super high resolution set of imagery, but it's adequate. And then the target, which is basically identified by the polygon. So just to help, these are some hints, and also Rachel has some more hints in there. So kind of do it this way to get yourself started so you're not frustrated, and then just fill in and you'll learn and see a lot. But basically I've shown BR, the bedrock, the QIA, and these data is really nicely shown by these dark ridge lines. So that's the pavement. So it's relatively smooth in texture, but also dark in tone. There's this interesting, you can even see a little bit of the geologic structure here, this tertiary basin fill units. Over here is a zone where there's some ridges that are above some lighter colored material that's basically QOA over tertiary. And then QYA is most of this lower, relatively smooth surfaces. What's important, and you'll see here as well as later, that the QYA can have a varying tone depending a little bit on the source material. So this is a grayish, mid-gray QYA. So up here in the top, there's probably some more QYA up in here, but it's lighter in color because of the source of the material and probably has a little bit of an aeolian input as well. So I'm just kind of giving you points here where you will build the polygons. And if we go down to the south east, there's a couple more QYAs. You can see they're basically probably would do them as the same polygon. Actually, Rachel maps this one at this dark gray as a single polygon, but it's, I think most of this relatively smooth surface is all mappable as QYA. It's just that the rock source is a little bit different. And again, if you were going into finer levels of detail, you could break them out, but I would lump them. Then you can see this little hill here with the QOA. There's some QIA, which are these what look like more isolated surfaces. They're no longer active and still fairly smooth. And then finally, the lower right has a couple more QIAs in there. And then QP, this is a little playa, a little closed depression with fine grained sedimentation. So for this assignment, lumping into fewer units is preferred rather than developing new ones unless you have time to apply it consistently across the area. See also the demo video from Rachel, because she basically maps this lower portion the way we think it ought to be done, just to help you get a jump on the assignment. Okay, what students do to distinguish between an alluvial deposit and an effluvial one? Good question. So in general, I would go with alluvial. You know, this is an alluvial fan environment where there's coalescing fluvial networks, kind of in a distributary mode. So I think I put a QF up here. Did I not? Actually, I didn't even. Oh yeah, there's one Q by F. So in this case, what I would say is because this is a little bit more of a channelized environment here, you know, this guy I would call as a QYF as being fluvial. But if, you know, don't fret about it too much. If you don't feel like it's sufficiently channelized, just call it a alluvial. It's much more alluvial than fluvial here. Hopefully that helps. And then what is the other hint here? Rich says, sometimes helpful to separate bedrock from quaternary, then fill in the rest. Also getting the QYA done earlier highlights areas. Yeah, so most of the area that will be covered in this is going to be either bedrock or QYA. And so that's fine, but it's not super interesting. We're looking for where there's disruptions and maybe some of the older material that might indicate prior fault rupture. Okay, so some more questions. Oh, that was Rachel asked the question, but Rich had a good idea.
Can I make two comments while people are
Yeah.
maybe thinking? So one of the questions asks you to go and find some data from the USGS and basically just show us that you found it. So just a word of caution, sometimes the USGS website doesn't work. So don't wait to the last minute to try that problem because you might run out of time. Second is the fault in this is not going to be quite as obvious as last time. And that might be frustrating at first, but be persistent, use this evidence and this approach that we've been talking about to give you a little more confidence, possibly in your work. Is we found last year that the student maps were a lot closer to both the ruptures as well as professional maps from people in the field, I think, than the students were expecting. So have confidence in what you're doing, even if you're just really not sure at the time.
Very good. So I think that's a good piece of advice that Chelsea has provided, is don't force a lot of faulting, because, you know, maybe background knowledge, you would say, well, this isn't on the plate boundary, so the rate of faulting might be relatively low compared to the rate of surface process modification. So if there's evidence of prior ruptures, it's going to be localized, just some little areas. And so you'd want to look for that, and look for the ensemble of features that indicate faulting. Any one relationship might be uncertain. I'll come to Mara's question in a second. I had a question from Isabella about scale, map scale. So this is sitting, you can see when I screen cap this, I'm at 26,000. So this is too small of a scale. And I don't know the scale of these, the next two screen caps, because I zoomed in on them. But, you know, my suggestion would be to, this isn't a terrible scale to work at right here. You can kind of see, you know, all that's here. So if I go back up, that's like a quarter of this. So quarter of this view. So I can't quite calculate, you know, I don't know, 1 to 10,000. I think, you know, in the interest of your own time and kind of controlling level of detail, you want to sort of operate at a relatively fixed scale when you map. You can always go back at a finer scale, but if you zoom too much, you end up forcing yourself to kind of have this heterogeneous level of detail. And so at least try to, when you're mapping, do it at one scale, and then you can decide if you have time or you want to go in and do a finer level pass. So the question, and then I'll open up for some more discussion. Also, Mara asks, can we go over geology interaction with faults? I'm not totally clear what you mean. What, you know, when we're talking about faulting here, we're talking about disruption of either the morphologic features or the superficial geology that could be explained by faulting. So disruption meaning ending, or kind of patterns that are not consistent with this relatively simple Piedmont condition here, where we just have a alluvial fan setting.
Yeah,
Rich, looks like you were gonna, oh, go ahead, Mara.
Oh, I guess like when you were talking about, when you showed the faults earlier in your lecture, it wasn't clear to me like how the geology ended, I guess, or the different like units ended, I guess.
Yeah,
I saw
so
the morphology, but
yeah, in this map, like here, this line that goes across the lower portion is the Mannix fault in the imagery, and so you can see there's a disruption of colors that's really defining basically the end of those bedrock units. But also we see a consistent kind of termination of the younger units at that same zone. And there's a kind of a sort of like each of these landforms sort of shows some change. Like, see, there's a narrowing here. This thing shows some weird kind of a deflection or something. This is like a little bifurcation. This is kind of stopping. So there's a lot of disruptions to the morphology as well as to the units as implied by the color and the topographic roughness that helps support an interpretation of a fault. You know, and I think the key thing is any one of these, you know, if you just zoom into any one of these relationships, you might be like, I don't know, it's kind of ambiguous. But if you see all of them together, you're like, well, you know, one explanation is that that's where the fault is. So that's why I say ensemble, you know, so it's not one, but taken as a whole, they would be explained by the activity of a fault. Rich, go ahead.
Yeah, also like fans have a fan shape, and so if you map a fan, say an intermediate fan, but it's only preserved in kind of a strange shape in a strange location, maybe kind of not next to the mouth of its canyon or something, you have to ask questions of, you know, why is that there? Or maybe it has a linear edge to it or something like that. that is not totally natural of the downslope deposition of a fan, you know. So look for, you know, sharp contacts, irregular shaped bodies of different ages of fans, and that'll start giving you an idea of where things may have been messed up from their natural depositional direction.
Yeah, thanks. And like I've been saying, I've been stressing is don't put the faults down first. Try to really force yourselves to decide where the faults are at the end. You know, it's sort of the psychological discipline of observations before interpretation, where at least in my view, the faulting is the last of the things we interpret. Even if you're starting to get an idea, oh yeah, I think it's right in here, but you know, kind of be patient, sort of force yourself to you know, build up the evidence before you draw where you are. And it may not have to be through going, it could be discontinuous, and that's okay. Okay, guys, so I have a couple more minutes here in this lecture, and so I'm gonna go. I wanted to just show a couple other things if there's no questions right now. So just as a reminder, because you know, people always, I feel like I'm constantly like always only giving California examples or something. So, and we're fortunate to have, you know, many people here, and we know that faults are around the world. So also this kind of mapping can be done elsewhere. So this is actually an example of a detailed superficial geologic map from Massachusetts, from coastal Massachusetts. And there's no faults in here, but I wanted you to just see kind of how things are described. It's the same thing, you know, beach face deposits, QB, thin till deposits, QTT, drumlin till. So every, you know, different landscape's going to have a different set of drivers. So in this case, this is a coastal environment that had a big glacier drive over the top of it 15,000 years ago, but still we can use the same kind of mental framework as far as how we're going to map these things. And so if you look, you know, this really pretty cartography, look at this is the, if anybody's been to Newburyport, this is right at the shoreline. This also has the offshore environment. So they had some bathymetry and maybe some side scan sonar to look at the, you know, seafloor roughness in that shallow environment. And so they're able to map the beach, this back shore environment. And I don't know all of the codes here. And these QTDs are drumlins, so they're sort of positive features from a last glacial advance. But this, you know, if there was a disruption to these features that could be explained by a fault, this is one way to find it and to prove it. So I just wanted to bring that to your attention, because the same concepts can be applied in other places besides the Mojave Desert. And the last part of this lecture is kind of a little bit more on climate. I'll just stick in there. But Rachel says, what helped me last year was to look at images of the alluvial fan without faulting to see what the natural progression on a fan should look like, and then see the disruptions more clearly in the mapping area. Yeah, so I think a key assumption that we are making is that there is a height difference, and that is that the older things are higher in the same relative piece of the fan, but the old ones are so high, they've been left high and dry for so long, they've actually started to erode. And so the intermediate ones are the ones with the best pavements. And then the Ys are basically the recently active surfaces, and they're relatively smooth and may even be aggrading a little bit. But this landscape, like many places in the world, has been incising in an sort of pulsed, or so let's say episodic incision over the lake quaternary is something we see in many places. Questions? What do we look at? Look at Google Earth. Just don't go to landers. Just that's in like central Mojave. Go somewhere else with alluvial fans. Go to Arizona, because we don't have many faults in Arizona. You can try to find a few. So, but just try to be strict. I think if you're struggling, you know, start with what we've given you, but also force yourself to you know, answer these questions about the patterns in the imagery, and then say, I'm just going to do it on tonal variation and texture variation and shadows, and that'll help me get my units defined. Like you can almost, when we write a description of geologic unit, if we're in the field, we describe it, based on some of its geologic properties, but in remote sensing mapping, we can describe it based on its image related properties. And that's a perfectly reasonable way to proceed and to find and to be consistent. And yes, these slides will be posted on the website, and the recording has already been linked here in the chat. So I have just 4 minutes. So I'll just turn things over to Rich, if that's okay, Chelsea, and we'll let him continue for the remainder, and then I'll pick up some things on Tuesday.
Yes.
Rather than feeling rushed. Let me just look here. Yeah, so there's a few. Ben Johnson gave us a nice lat long. Then Chelsea's reminding us that these slides are always available pretty much as soon as we can get them online. So with that, I'll stop and I'll turn it over to Rich. I'm going to be listening. I'm just going to get some coffee in the other room. But
yeah, go ahead. There may be a few minutes at the end for some additional discussion if I finish up a little early. So let me share my screen. One second. Just pop off here in a second. There we go. Everybody see that all right? Okay.
Looks good.
Your message in front of my screen, but I'm going to go with it. Okay, so I'm going to talk a little bit about mapping tectonic fault. That's the title of the class. Mapping examples from Alaska and Northern California, mainly along the Denali Fault, along Western Projection and the San Andreas Fault. These are two major strike slip faults. The San Andreas moves at about 35 millimeters per year, and the Denali Fault moves at about 10 millimeters per year, so about a third of the rate of the San Andreas Fault. But as you'll see, the morphology is very similar along strike slip faults, with a lot of landforms and features that are common no matter how fast the fault is moving. So this picture is from the Denali Fault, which is behind the survey instrument running along the base of near this little hill, and there's a helicopter coming in to pick us up. Okay, I'm going to start with the San Andreas Fault. Oftentimes along strike slip faults, you get these major, sometimes we call them rift valleys or linear valleys. So this map is a CEM, and the zone that we mapped in is marked out by these black lines. The fault is shown in red, but in the landscape, it's this massive valley that goes for a long ways along strike. And another common feature is some places there's saddles. So in this case, the Garcia River follows along strike up here, and then it goes up into the mountains. And then the Gualala River comes down out of the mountains and then flows south. And so we call this a wind gap. Sometimes there's terraces or fluvial terraces, like in this case here in the saddle itself. But and the fault trace goes up and over it. But it's the long-term motion of the western side versus the eastern side that's created this big rift valley. This map below just shows the distribution of the rivers draining out of the coast range and then hitting the fault and moving south along the Gualala and moving north along the Garcia. This picture is sort of an air photo, slightly oblique, looking north along the Garcia River. So the river valley is prominent the river valley is prominent. You can see it here. But you also notice there's other lineaments within the rift valley itself, which could be secondary traces. So here's an air photo, and it just illustrates the density of trees, makes it difficult to map on air photos for fine scale features. However, the fault is still pretty well expressed coming through these photos. And the river kind of meanders around, but generally follows the rift style. Okay. So we've been talking a lot about GIR, and I mentioned an old sort of napkin version of that on the Bainbridge Island. We got better at it through time. And in this, I'm going to show some examples where we walked about 28 kilometers of the fault, and we kept track of site numbers from field sites, and then track of sort of which reach of the fault. So this is 3 kilometers south of Annapolis Road to Buckeye Creek. And these are all the features in that zone. And then Buckeye Creek to Big Tuckerwood Creek. So then we had another zone. So we talked about dividing up the fault into 1 kilometer sections and evaluating the quality of the, features and the confidence of the fault traces within certain zones. So this is sort of an early way of doing that. And then up here is just sort of an early version of geomorphic indicators. So here's a table here that lists them, and some, if you looked at the handout that was online, there's different things: scarps, ponds, swamps, saddle springs, linear valleys. All these are features along a strike slip fault, and you can make up some descriptors of your own sometimes. In this case, we divided the scarp into northeast facing and northwest facing scarps. So often along strike slip faults, you'll have oppositely facing scarps along strike. It's not always one side up. Here's a picture of just a linear valley here with a scarp here. And it just goes to show how densely forested it is and really difficult to see. This is only about 1 meter high, and probably along the 1906 ruptured trace. It's just a linear trough with an uphill facing scarp. So the western side of the fault will be up here off the picture because of that. So here's some of the first, so I mentioned that the Bainbridge Islands was some of the first LiDAR used in neotectonic work. This is sort of the next realm of it. A few years later, we got LiDAR on the northern San Andreas Fault. And now there's much better LiDAR in this region. So there are some artifacts and processing and some thinning here that are hard to interpret a little bit, but this is some of the original LiDAR. You can see some of these dirt roads in here. There's the logging area, so there's logging roads all around. But what you start noticing is sort of this northwest grain of shadowed slopes, and these are little scarps along the fault. And so you notice right here where my cursor is, there's a little left step and other left steps. So left stepping and echelon features or sort of overlapping fractures are a common feature along strike slip faults. And left stepping and right lateral systems, and right stepping and left lateral systems, but they happen at all scales, at the mountain scale and then at the microfracture scale as well. So here's sort of a slope shade. This is overlaying from the LiDAR, overlaying with a topo map. And this is just an example of the different features that were picked out. And I know it's hard to read, but each one of these has a site number and then a symbol as to what geomorphic feature was there. And then also the confidence is shown up here, where inferred or strong or weak, similar to our fault confidence that we're working with for this class. So here's an example of a sag pond and also an uphill facing scarp. So the dashed line is basically approximately where the fault scarp is. So there's a little uphill facing scarp to the right of the fault here. It's about 1 meter or 2 high. And then this big long slope to the left here is a east-facing slope that's pretty steep and tall. And so this is part of the fault valley, and it's common for streams coming down this mountainside to pond against this uphill-facing scarp. And so the uphill-facing scarp move is quite common along this part of the San Andreas Fault. So you get sag ponds, you get ponds, not necessarily structural sag ponds, but you get ponds along the linear valley and a lot of uphill facing scarps that are really clear on the LiDAR. So here's just another example, and I'll just point to it so your eyes can be drawn to it. It's this little thin dark gray shadow moving along here is sort of the fault valley there, and that's mapped in here. There's a few strands parallel to it, but then the river's following the Rift Valley. But you notice that the fault's not in the bottom of the valley itself, it's along the southwestern wall. And then here's just another example of the same sort of thing, where you see this little gray shadow along the southwest wall of the valley, and that is the trace of fault. Okay. And again, it's been divided up into solid, strong lineaments, inferred lineaments here, where it's going across the young alluvium of the Gualala River. And then we have these features marked out all along. And so the more of these features you have, the more confidence you have that you're on the active fault trace. And so this is how we reported it there. So as I'm talking, I kind of like get a little bit behind in the chat. So feel free to stop me anytime that anything comes up. But I'll move on to Alaska now. The Denali Fault is a very impressive strike split fault. Like I mentioned, it moves at about a third of the rate of the San Andreas Fault, but we see a lot of the same features. And so I had this image of Alaska with the faults on it, the red, the quaternary fault, when I was talking about crest and reverse faults. I talked about the Castle Mountain Fault here in southeast Alaska, and I also talked about the Northern Foothills Fold and Thrust Belt, which is on the north side of the Alaska Range. So here's a zoom in of the Alaska Range here, and the Denali Fault makes this nice big arcuate scar across Alaska that separates interior Alaska to the north from southeast Alaska to the south. And one thing that's really important to understand is that as the fault makes this big bend, it's a big left bend. Slip is transferred to the north onto these reverse faults on the north side of the Alaska Range, and that's partly responsible for this huge, for Mount Denali and how big it is, and the rugged topography of the Alaska Range in this region. And we're going to do a project on the Denali Fault, so I'm not going to talk about historic earthquakes on the Denali Fault, but show some examples of the fault morphology. The Park Highway, getting close to Denali National Park. This is IFSAR data. I think it's 5-meter data on the top, and then a geologic map on the bottom. So it's just an example of the geologic mapping that Ramon was talking about, where we have ice scoured bedrock and some glacial moraine in the high country, and then getting into younger deposits with rock avalanche deposits, different ages of stream alluvium, old and young, and some sand deposits. Again, there's a big valley coming along here, like the San Andreas, somewhat of a rift valley, and I don't have the bedrock on here, but these big bedrock are different bedrock than what's on the other side. So it shows long-term displacement along the fault in the right lateral sense. And I think the cumulative displacement is about 150 kilometers. And this fault right here was mapped in the field, but we did a lot of work mapping prior to going to the field, doing the types of stuff we're doing in this class. So I'm just going to go through some photos because it's pretty spectacular, and it's kind of hard to see the fault on the fan surface here. There's some cracks in it. So this is a really young fan. Sometimes in air photos, the snow can give you an idea where the fault is, because the wind will blow it and it'll accumulate at the base of a scarp. This is like an oversteepened scarp here on both sides of this fan. And then here's the interpretation on this side. So sometimes when ruptures come across very young, unconsolidated material, they break up, and so then there's these sort of left stepping and echelon fractures going across it. So I mentioned air photo mapping. So here's an air photo on the left and then an interpretation on the right. Ramon was talking about breaking out different units. So I've broken out this fan here. This is just Mylar and pencil, just over the photo. It gives an idea where to go in the field. But this fan right here is on the uninterpreted is this one here. And what you can see there is we look for these dark tones that are going sort of 90 degrees or across the general flow of the fan. So when you look real close, you start seeing these dark lines coming across. So this line right here would be interpreted as a fault here, and then it sort of splits apart a little bit into a couple traces here. There's two traces. You can see where my cursor is. There's one on the north and one on the south. That would be these two traces interpreted here. And then it goes across this fan, and it gets a little chaotic with some left steps and moves across. So here's another one. This is a rock glacier, and this is a fan. I'll show some details of this fan in a second. But again, it's just like looking for these dark tones going across the grain of sediment transport, which are fans coming out of the mountains, north to south. And then east to west, we have these different lineaments that we can interpret with our different confidence ratings. Here's just an air photo interpretation of where I map the faults coming through there. So again, right here where my cursor is, it's pretty clear that there's two traces there. And that's interpreted right here on the interpreted version. Okay. Okay, so in air photos, sometimes, okay, yeah, this fan looks like it has a fault going across it, and also looks like it has a little right lateral displacement. So the western edge of the fan is really steep mountain front right here, comes down on that steep side step to the left there across the fault. So there's a little right lateral separation. So we find this in the air photos, say, okay, well, that's somewhere where we could do some work to understand the slip history. So here's that fan again. Here's the margin of the fan here, and then it steps over here. There's these nice lineaments going across the fan here. Another thing you notice is sort of the stream network, the drainage network on the fan is disrupted. We talked about in Wallace Creek beheaded channels and stuff. So there's a number of beheaded channels and also a channel offset. And today this fan is isolated. So avalanches, debris avalanches come down and they go around to the right. And so the fan is no longer getting much deposition, maybe a few rock faults here and there, but it preserves this record of stream channel offset. So you can survey that with the differential GPS and make a hillshade and see the channels coming up. The scarp shows up really nicely, but also a secondary scarp above it shows up pretty nicely as well. In a slope map, these channels show up pretty nicely too. So there's three nice channels here, another sort of less defined one here, and then sort of the last most active channel has an offset in it, and now it's all abandoned. So here's that air photo of that same site again, showing two traces coming in, and this trace on the north sort of dying and stepping onto this more primary trace here. And this is what it looks like from pretty low altitude near from a helicopter looking down, and there's this channel, and it's offset about 7 meters to there. And there's also an uphill facing scarp going across there. So sometimes it can be really clear, like in the case of that fan, and sometimes it can be really subtle as well. So this is a glacially scoured landscape. This is a moraine coming out, this lighter colored material coming out of this valley. So ice was, far down this valley, probably as recently as 8,000 or 7,000 years ago. Okay, it lasted a little bit longer up there after the last glacial max. But anyway, here's a bedrock saddle that's along the strike of the fault, and there's just this subtle little trough going across the saddle. So sometimes it can be really subtle to find the fault. Other times it can be pretty dramatic. So here's west of the Parks Highway in Denali National Park, and the darker green here is a stream channel. So the stream, the long-term offset of the stream channel is right lateral. You can see where my cursor is dragging, and then the fault makes a nice sharp screaming lineament going across the landscape with ponded water here and here, and this is a zoom in of the one up here on the eastern side from here. And this scarp here is about 4 meters high. It's uphill facing, and there's ponded water along it. And it may actually be a true structural sag pond, because there may be actually a lineament running along the backside of the pond here as well. We know that just from at it in the field and on air photos in detail. But it's a pretty impressive feature, and it's, you know, pretty obvious when you see it slicing across topography, has right laterally offset drainages, and also some juxtaposed topography, like this bedrock knob here sort of seems a little bit out of place as compared to what's on the other side of the fault. This is a nice dramatic example of the beheaded channels, offset streams. They're not really active streams, they're kind of like snow melt, avalanche channels, they're high energy. So what you can see on the right side here is this one has broken through the scarp and is now, you know, will carve its own channel for a little while until there's an event where the south side moves to the left and the north side moves to the right, and we abandon these channels. There's a number of them along here, and it's also a linear valley with an uphill facing scarp along that range fence. So more linear valleys here, just more from the ground. So they can be, they're really striking on air photos, really linear, they show up really well, but in the field, they can be somewhat subtle. I mean, if you're in the field here, you know this is a little linear trough here, but it's not that big. It's about 1 meter high right here. For a pretty major fault, it's a pretty kind of a small feature. It's a major feature in that it goes along strike for a long ways, but it still can be fairly subtle. Sometimes the troughs are bigger. So this is geologist Dick Rieger walking down the fault trace here. So this is an uphill facing scarp, a south facing slope on the right side of the photo here is going down slope, and you have an uphill facing scarp. So really common features are these linear valleys and uphill facing scarps. Then moving farther out west, the Denali fault, because a lot of the slip is transferred to thrust faults north of the Alaska range, its slip rate diminishes quite a bit. You get out west, it's down to about 5 millimeters per year, but still we see striking features going across the landscape. So this one on the left here, there's a slight right displacement of this channel here. So this is like either a glacial outwash terrace or a fluvial terrace. And there's a vertical scarp going across it as well, going left to right across the photo. So again, right descent of this abandoned channel and a vertical scarp. This photo on the right, we have two different ages of sort of fan surfaces that have come off the mountains here, where this older one in the middle of the photo has a larger scarp, and then the fault is running from the upper left to the lower right. And so this is another fan surface that is inset into this older one. And the scarp is much smaller and a little more fragmented going across it. So this fan has experienced less earthquake than this one here. Okay, so I just put this travel photo in just because it's kind of cool. It's hard to get there, it's very remote, a lot of planes and helicopters. But here's the helicopter for scale here with some geologists standing on top of the scarp. So it's a pretty large scarp here, about 4 meters or so. But what you'll notice also is there's a smaller scarp along the base of it. So the most recent earthquake would be generating this smaller scarp, and then the cumulative height of this scarp would be the result of multiple earthquakes. The photo on the right here is, we talk about linear valleys and sort of juxtaposed bedrock topography. So there's these two ridges here that are bedrock with a little linear valley going between it and this higher bedrock topography on the other side. So we would infer the fault was coming through this side. And check the time, doing okay. So and then I wanted to put this in here too, just to bring it back into context of what we're doing for the class. We want to understand sort of where we can predict where fault ruptures might happen. This is a gas pipeline project along the Park Highway shown in yellow. In these two images on the right, one is interpreted and one's not. But what you can notice on the top one is there's linear valleys like along the left side here that are very clear and prominent. There's another sort of clear lineament right along the cursor here. It comes down, but the Jack River and the Nenana River, are very powerful rivers and active on their entire floodplain, and evidence of the faulting is gone or covered or eroded away. So it becomes pretty difficult. There's also a secondary liniment on this little bedrock knob here that could be an active fault as well. That's shown interpreted right here. So the image on the bottom is the interpreted sort of solid lines where we know where the fault is, strong, confident, and then some light, small dashed lines and some larger dashed lines showing kind of a range of where the fault could project to and sort of where we prefer that it would go across. So this comes into play with engineering design of the pipeline. They only want to design for a certain length of pipeline because every length that they have to do special design to costs a lot more money. So it's a cost benefit analysis thing that they pay geologists to figure out to reduce the uncertainty for how long of a zone would need to have that special design.
And just to
so,
bring it back to our project, part of the work that we're ultimately trying to help PG&E do is exactly that problem. How well can geologists anticipate the location of fault before a rupture?
Exactly. And so this last image up here is the LiDAR, and you see this sort of oval shaped high spot, okay, and then a linear valley. This is just topography that's juxtaposed along the fault, comes down, and it actually makes this you can't see in the LiDAR, but in the field, a bunch of left stepping and echelon fractures across this glacial outwash terrace. There's some landsliding on the edge here. And then, so that's where the last location on the east where we know where it is. And then the various projections of the strike of the fault, trying to connect it with fault on the other side of the valley. And then the red box is kind of like this preferred zone of deformation that we can recommend is, yeah, that's where we think the fault would come through. And then we do geophysics in the valley and different things to help kind of tie that in a little tighter. But anyway, I think that's all I want to say about that. It's just a real world application for understanding the width of deformation and where the active fault traces are. And that is, I believe, all I have. Yeah. So
Thank
I will
you.
open that up for discussion. We have about 5 minutes left. I can go to any photos that you like. Or
I got a question, but maybe let's try to get a few student questions first.
I'll save my screen sharing on in case we want to go back to any of these photos, but they're just pretty dramatic examples of strike slip morphology. And this one's one of my favorites. And we see these types of things all along the San Andreas Fault. You know, we saw these abandoned channels at Wallace Creek. It's just a really similar thing. The streams come down and they get beheaded, they get pirated. They contribute water to ponding along fault valleys, etc.
Hey, Rich, maybe can you, there's a bunch of stuff I was excited about, but just maybe while we're waiting for some questions, can you go back up to the San Andreas to see that GIR? Just leave that there for people to stare at, the like slide 4 maybe. Just so people start to, yeah, that's kind of, I think hopefully people get it in their mind. This is a really great example of what we're trying to do. And the only addition we've made is to really try to give each of those features some kind of a relative scoring so that, you know, you could somehow quantify the strength of the feature in a by segment. So anyway, I don't want to interrupt if other people have questions. I just thought we could ponder that.
Yeah, and dividing it up into sections is something we didn't do here also. We have different confidence that's quantified by kilometer section based on
So this
how
question, why 1 kilometer? I think it's just kind of convenience, especially given the typical map scale. So you can see here, Mara, like that lower scale on this figure is 500 meters. So it would be, you know, kind of a convenient way to divide up that area by, you know, there's about 1 kilometer and maybe there's a second one. So it's it's something that's tunable, but it's sort of it's probably trial and error. This is what we're trying to learn. Obviously, if you break it up into too small of pieces, you don't have enough GIR to score. But then if it's too big, you're not getting that relative sense of confidence. So it's a little bit trial and error. But given the information density, it seems like this kind of mapping supports the 1 kilometer well.
Cool, thanks. So just to be clear for the assignment, you don't want us to map faults that are less than 1 kilometer long?
No, you would just put that in 1 kilometer.
Sorry, can you explain that again?
Well, if you have a 100-meter long scarp and that's all there is, then that's all there is for that kilometer. So we just don't want to discretize that finer scales than 1 kilometer, but it would just say that in that particular kilometer, there's not a lot of information because this short little segment is all that's there. So, you know, it'd be kind of like, go ahead. No,
I was just gonna say, but like in the middle of this, there's a bunch of parallel traces as well. So in your 1 kilometer section, you would have sort of a main primary trace and maybe some secondary ones or something like that as well.
Yeah, and that's what we're trying to also learn. I think as far as, you know, developing this approach is what works. Like this piece right here is pretty simple. Like we could get a good score for that and be pretty happy about it. You know, Mara, like you're saying, like this little thing here, if you still put it in the 1 kilometer, it's not going to weigh as much, but that makes sense, right? Because there's not much to it. So it's sort of, we're getting out of it what we're intuitively expecting, which is in this case not circular, but trying to help design the approach, I guess.
So also to get some sense of the sort of average representation of the fault, and if it's too detailed, then it's harder to step back and make some of these larger scale conclusions about what's happening. Maybe along Chrissy's question though, exactly where you put those breaks, still up for geologic or geologist interpretation, and so it could, example here, vary based on fault geomorphology, or if there's rivers that change and for some reason make you want to, you can then use those to break up the faults.
Yeah, when you are doing the assignment too, you will have all your fault traces already mapped. So you can either start at one end of the trace and start measuring out the 1 kilometer segments, or if you see a very large natural break in the topography where, you know, there might be a strong segment that directly feeds into a concealed like active alluvial channel that's covering all the evidence of it, you can break it before that. So it would make more sense based on the evidence.
Yeah, I think a couple comments. One is Aaron said, well, what if you see something good, should you put more points there? And the answer is actually no. You need to try to be even. Otherwise, it kind of defeats the power of the GIR's ability to kind of discriminate in a relative sense between the different traces. So try to be even if you could have a feast in one area, but then, you know, you would definitely pick the high quality features there. In terms of gerrymandering and so forth, I think there's 2 points. One is, as you guys said, is a geological intuition of obvious, you know, breaks that mean something, like steps, bends, transitions in bedrock geology. But the other thing is it's easy to program, you know, sort of a range of different ways to segment the faults in the GIS kind of after the fact. So I would say don't fret too much about exactly how that ultimately is done, because we could do it 100 times, each time starting 100 meters further down, just, you know, do a rolling average or something. So don't worry about that too much. I think just now
That's
get the
the
points
easy
in.
part. The geologic
Yeah.
intuition is the harder part that we're looking to get in this class.
Then one more comment, don't be afraid of lineaments. We map lineaments all the time. In this example here, there's a few sort of subtle lineaments from the LiDAR over here, and they got dotted traces on this map. But, you know, what the final product is always going to be evaluated in the field and stuff like that, and you may determine something was, you know, not a fault. But don't be afraid to map lineaments and give them a, you know, a low confidence or a weak expression or something like that, because they could very well be false as well.
Aaron asks a good question. If there's a clear scarp, should we preferentially label scarp along the fault, or should we add in less obvious but supporting features? So in that case, you would want each place where you do see a clear scarp, you would want to add a GIR feature there. And you would certainly also want to include the other pieces that you see. And later, how we would count multiple scarp features is up for discussion. But yeah, as Ramon says, that you do want some even density expression.
And maybe one final comment, sorry, Christy, and is also, you know, the expectation when we look at a map like this is if there's blank areas, there's not a fault there, rather than you didn't look. And so I think it's useful if you're going, you know, either to, you know, kind of like Rich said he saw actually a couple more features in here, but basically, you know, NF, there's no fault, you know, no fault. That means you looked, or, you know, otherwise we wonder, well, has that been mapped, you know? And it's okay if it's not. You could also just draw a box around and say, well, this was the area of emphasis, so be outside of that, we don't know. But I do think it's worth, kind of having that coverage be even. That's why I keep emphasizing that. You can't have a try to minimize heterogeneity of observation density. Otherwise, when someone reads the map, they don't know if you just didn't look very hard there, or there's actually nothing there. Christy,
Like,
go ahead.
For example, right here, you might say, oh, possible right offset of this channel. But then if you know, if you mark that and you don't see any other features along strike, you know, to the northwest or southeast of that feature, you may have more confidence saying it's not a fault. But you know, someone's not going to be able to say, oh, but you have a right lateral offset. Why is there not a fault over there? So
Because there's nothing else.
Observation.
The ensemble is modest, if not limited to a single element. Christy.
So one of the geologic practices that's in Canada and the UK is like when you're filling in an area of like, this is your unit, they will shade the unit color a tad darker in the places where they actually saw rock. And that's really important in places where your outcrop area is like maybe 2% of your total area or something like that. So then you know that everything else is inferred. And most of the actual contacts between units end up in the inferred area. So that's like really important to know that those were not mapped, they were inferred, and the rocks were not seen close by them. So like Rich pointed out that there's like a potential spot there, but there's no spot on the map that shows that like, here's a weak indicator that didn't pan out because we don't have a lineament of weak indicators that then would like elevate that to like mapping a possible fault. So like for completeness, I guess that, yeah, the problem is the difference between unmapped areas and areas where you looked, but you didn't see the feature that you're after is not clear unless you explicitly build that into your mapping scheme. And that's like a really important distinction. Because did Ian say earlier in the chat, like absence of evidence is not evidence of absence. And like there very well could be a fault there, but it just didn't move in the last 5,000 years, but the surface crept. You know, there's like all this soil creep in the northern San Andreas. So like it definitely could be an evidence of long-term offset of that drainage, but like not recent.
Totally
So
agree. And we just tried to eliminate some of those in making a final product, you know.
Right.
We did look at them, and it's not necessarily all reflected on this map, but this is our final.
That goes into the invisible layer of science between like all the stuff you have to do to know something and then how much of it you actually end up publishing. Yeah. But I wonder if,
we are
you know,
out of time. Sorry, I didn't mean to cut you off, Christy, but yeah, we're overtime, I believe. So thanks everybody for sticking around and having a fruitful discussion. Hopefully we can continue it next time a little bit. Anything else, Chelsea, Ramon?
Just posted office hours. Students, please take advantage of these opportunities to meet with me and Rachel. And if you're having trouble on the homework, really, you have no excuse to not go. And they're happy to help you discuss how to make better fault maps. So thank you and see you on Tuesday, if not sooner.
Thanks. Can we capture the chat?
Yes.